Welcome to a video that will show how to determine the parametric equations of a tangent line to a curve that is defined by a vector valued function. Let's start off by reviewing the parametric equations of a line in R3. A line that is parallel to the vector v that has components a, b, c that passes through the point x sub 1, y sub 1, z sub 1 is given by these three parametric equations. So what I want you to notice here is that the vector parallel to the line with components a, b, c give us the direction numbers for the line given here as the coefficients of t. And then the point on the line, as we see here, would be the point of tangency having coordinates x sub 1, y sub 1, and z sub 1. So in order to determine the parametric equations of a tangent line to a curve, we'll have to determine two things. We'll first determine the point of tangency, x1, y1, z1, and then we'll determine a unit tangent vector, or at least a tangent vector, and the components of that tangent vector will give us a, b, and c. And again, one more thing to review. In order to find a unit tangent vector, we need to find the derivative of the given vector valued function and then divide by the magnitude. Again, we don't have to find the unit tangent vector. A tangent vector will do, but it is common to determine the components of the unit tangent vector instead of just a tangent vector. Let's go and look at an example. When t is equal to 2, we want to determine a set of parametric equations of the tangent line to the given plane curve. Let's first determine the point of tangency when t is equal to 2. And that would be the terminal point of the vector produced by this vector valued function when t is equal to 2. So the x component would be 2 squared, and the y component would be 3 times 2. So the vector would be 4, 6, which means the point of tangency would be 4, 6. And now we need to determine the direction numbers for this tangent line, and that'll come from the component form of the unit tangent vector. So let's find the unit tangent vector valued function and then evaluate it when t is equal to 2. So the derivative of r would be 2t, 3, and the magnitude of this would be the square root of 2t squared plus 3 squared. So we'd have 2t, 3 all over the square root of 4t squared plus 9. Again, this will give us the unit tangent vector. We could just use r prime of t to find a tangent vector that's not a unit tangent vector. So let's go ahead and evaluate this at t equals 2. So we'd have 2 times 2, that's 4. The y component would be 3. Then we'll divide by the square root of 4 times 2 squared, that's going to be 16 plus 9. Square root of 25 would be 5. So the unit tangent vector at t equals 2 would have an x component of 4/5 and a y component of 3/5. So now using the point of tangency and the components of the unit tangent vector, we can determine the parametric equations of the tangent line. We would have x of t is equal to 4 plus 4/5 times t, and y of t would be equal to 6 plus 3/5 t. Now remember, parametric equations are not unique. What I mean by that is notice that we use the direction numbers 4/5 and 3/5 because these came from the unit tangent vector. Well, the vector with components 4, 3 would be a tangent vector, not just a unit tangent vector. So we could also have said x of t is equal to 4 plus 4t, and y of t could equal 6 plus 3t. These equations would give the same tangent line. Let's go and take a look at that line. In blue, we see the graph of the plane curve, and in red, we see the tangent line. But what we're going to see now is the unit tangent vector approach the value t equals 2. It's this purple vector here, with magnitude 1, and notice that when t is equal to 2, that unit tangent vector is right on the tangent line, verifying that the components of this unit tangent vector would give us the direction numbers for that line. Let's go and take a look at one more example. Here, when t is equal to pi over 4, we want to determine a set of parametric equations of the tangent line defined by the given vector valued function. Let's begin by finding the point of tangency by determining the vector produced when t is equal to pi over 4. Here's the 45, 45, 90 right triangle that we'll use to evaluate these trig functions. The cosine of pi over 4 is going to be 1 over square root 2. Sine of pi over 4 would be the same, and the z component is pi over 4. So the x, y, and z components of this vector give us the point of tangency. Of course, we could rationalize these, but I'm going to go ahead and leave it in this form. Now let's go ahead and determine the unit tangent vector valued function. So we're going to find the derivative of r and then divide by its magnitude. So derivative of cosine would be negative sine t. Derivative of sine t would be cosine t. Derivative of t would be 1. We're going to divide by the square root of negative sine t squared would be positive sine squared t, plus cosine t squared would be cosine squared t, and then 1 squared would be 1. Remember that sine squared plus cosine squared is equal to 1, so we can simplify this. It would be negative sine t cosine t 1, and the magnitude would be the square root of 1 plus 1, or the square root of 2. And now we need to evaluate this at t equals pi over 4. So instead of having this denominator here, I'm going to go ahead and write it as 1 over square root 2 times the components of this vector. So negative sine pi over 4 would be negative 1 over square root 2. Cosine pi over 4 is positive 1 over square root 2. And then the z component stays 1. Now let's go ahead and perform the scalar multiplication here. So we're going to have negative 1 over 2, or negative 1/2. For the y component, we'll have positive 1/2, and the z component will be positive 1 over square root 2. Now that we have the point of tangency and the components of the unit tangent vector, these will give us our direction numbers. We can now write the parametric equations for the tangent line. X of t would be equal to 1 over square root 2 minus 1/2 t. Y of t would be equal to 1 over square root 2 plus 1/2 t. And z of t would be equal to pi over 4 plus 1 over square root 2 times t. And as mentioned before, these parametric equations are not unique. Let's go and take a look at this graphically as well. So what we're seeing here in blue is the space curve. In red, we have the tangent line. And again, notice that the unit tangent vector here in purple coincides with the line, verifying that the components of this vector do give us the directional numbers of the red line. Okay, hope you found these examples helpful. Thank you for watching.